So, we are looking at phase response, and let us look at one more aspect. So, we have seen this simple single zero system before. Now, let us consider another related system, and A in general is a complex number. Therefore, this is 1 minus r e to the j theta z inverse. So, consider a related system let us call this g of z, and this is minus a star plus z inverse. If you look at h of z, the coefficient vector is 1 comma minus a. All I have done is I have just taken all the coefficients and made them as a vector, and clearly this is 1 comma minus a. And now let us look at the coefficient vector in this case. This is clearly minus a star comma 1. So, what is happening here is we have taken this coefficient vector and done two things. One is complex conjugate it, the other is time reverse it. So, we have time reversed and complex conjugated it, and then if you did that you will get this. So, you can think of g of z as taking the coefficient vector of h of z, complex conjugating it and time reversing it. And this clearly, because if a is r e to the j theta, this is minus r e to the minus j theta plus z inverse. Now, let us look at the magnitude squared frequency response of this related system. So, this is nothing but g of z evaluated at e to the j omega times its complex conjugate. Therefore, this is minus r e to the minus j theta plus e to the minus j omega times its complex conjugate. Therefore, this is minus r e to the j theta plus e to the j omega. And now, if you simplify this, what do you get? Yeah, I think you need to push pen on paper and simplify. 1 minus 2r cos omega minus theta plus r squared. Okay. And this is it something you have seen before? So, this is exactly magnitude of h of e to the j omega whole squared. All right. So, clearly the magnitude response is identical, and if you recall, the phase response of the earlier system is tan inverse 1 minus r cos omega minus theta, numerator is r sin omega minus theta. So, this is the phase angle. So, this is just recalling what we have seen earlier. Now, what about the angle of the related system. So, this is nothing but tan inverse imaginary part by real part. So, if you now look at this, so the denominator will be cos omega minus this will be r cos theta, and the numerator is the imaginary part. So, this is nothing but r sin theta minus sin omega. So, this is the phase response. Clearly, the phase response is different. The magnitude response is identical, phase response is different. Let us also get a feel for what the pole 0 plot is. So, in the earlier case, for h of z, you had a trivial pole and then you had a 0 at r e to the j theta. So, this is r and the angle is theta. Note that g of z is minus a star plus z inverse. So, this is the related system. What I have plotted here is the 0 of the earlier system, which is h of z, and this can be written as minus a star times 1 minus 1 by a star z inverse, simple rearrangement of the term. If I take minus a star outside, I will get this, and the 0 therefore is at 1 by a star. The 0 is clearly at 1 by a star, and 1 by a star, if a is r e to the j theta, 1 by a star is 1 by r e to the j theta, and therefore, for g of z, the 0 is at 1 over r e to the j theta, that is, it is exactly at the same angle, but the 0 location instead of being at r, it is at 1 over r. Therefore, I have the 0 here. Therefore, this radius is 1 over r, clearly it is at the same angle. And what we have done here is the 0 is at its reflected position, where the reflection happens about the unit circle. We are reflecting things with the unit circle as the reference, and hence if we had r e to the j theta reflecting around the unit circle will give you 1 over r e to the j theta. So, this is what is happening here. Now, to get a feel for this, let us consider a numerical example to illustrate this. So, suppose you had 1 minus half z inverse. So, this is similar to 1 minus a z inverse with a being half, and we have seen the phase response of this. So, if you plot the phase response, it will be something like this. This is how the phase response will be. And for this given system, the related g of z is minus half plus z inverse. And if you plot the phase response of this, the response will be something like this. All right. And one way for getting a feel for this is, remember, omega equal to 0 corresponds to z equal to 1. Therefore, if you put z equal to 1, g of z turns out to be half, and the phase angle of the quantity half is 0. Therefore, the phase response is 0 here. And if you put z equal to minus 1, which corresponds to omega equal to pi, so this turns out to be minus 3 by 2. Minus 3 by 2, the phase angle is pi. Therefore, at this point, it will hit pi and this will be minus pi. So, this is what the phase response will look like. I can also show this in MATLAB. So, if I will use MATLAB's inbuilt frequency function and then illustrate this. So, the first system is 1 minus 0.5, and then the denominator is 1. I am going to evaluate this at 1000 points. Freq z by itself will plot both magnitude and phase. So, this is what the plot is. So, this is the phase response, and clearly you see the rough sketch I had drawn here. So, this is plotting from 0 to 0.5. Another thing you need to pay attention is, I may have mentioned this before, MATLAB always maps pi to 1 rather than pi to half. So, this is from 0 to half in the conventional notation, and this is exactly what I had drawn earlier, the rough sketch. And if I now do this, minus 0.5 and 1. So, this is exactly g of z. Let me plot it in a separate figure so that you can compare both. So, now if you look at this, so this is exactly what I had drawn here. Therefore, the phase response is quite different between g of z and h of z, even though they share the same magnitude response. Now, just one more example. Suppose h of z is 1 minus z inverse. Now, the 0 is at z equal to 1 on the unit circle. Therefore, you can expect the phase response to be precisely linear, and you will have a jump of pi at omega equal to 0. Therefore, we have seen this earlier. So, this is the phase response. You have a jump of pi at omega equal to 0, and everywhere else the phase response is linear. So, this is the phase response of h of z equals 1 minus z inverse. Now, the corresponding g of z, by the way, this phase is pi by 2, this is minus pi by 2, and g of z is minus 1 plus z inverse, and this can be written as minus 1 minus z inverse. The reason for writing this in this form is, if you write it in this form, you see there is a multiplication by minus 1, and therefore the phase change will be pi, all right. And if you plot the phase response of this, it will turn out to be this. And what is basically happening is, this changes phase by an amount of pi. Therefore, this shifts up by a value of pi, and this has to shift down by pi. Therefore, the curve in red corresponds to the phase response of g of z. So, these examples illustrate that even though the magnitude response remains the same, the phase response is drastically different. Let us continue with what we observed now, namely, if you have h of z and you form g of z by taking the coefficient vector of h of z and then complex conjugating and time reversing, the magnitude response does not change. Now, let us consider the following system. So, h of z is 1 minus a z inverse, and the numerator is minus a star plus z inverse. Therefore, h of e to the j omega is 1 minus a times e to the minus j omega, and this is minus a star plus e to the j omega. I can take e to the minus j omega outside in the denominator. Therefore, this becomes minus a plus e to the j omega, all right. And here I can write this as minus a plus e to the j omega complex conjugate. So, this immediately implies that h of this is 1. You could have also inferred this from our previous argument. 1 minus a z inverse and minus a star plus z inverse have the same magnitude and magnitude squared responses. Therefore, the ratio must be unity. So, that is one way of seeing this. The other way of seeing this is by this manipulation, and this is a very important kind of filter. If you plot the frequency response, if you plot the magnitude frequency response, it will all be 1 between minus pi and pi. And this is called as an all-pass filter. All right, because it passes all frequencies. And this can be generalized. So, let me call each n of z as the nth order all pass system. So, denominator I have 1 plus a1 z inverse plus a2 z to the minus 2 plus a n minus 1 z to the minus n minus 1 plus a n z to the minus n. And let us apply the idea that we pointed out for the first order case. There what we said was the related system takes the original system, forms the coefficient vector, time reverses it and complex conjugates the vector. So, the denominator vector here is now 1, a1, a2 up to a suffix cap n. So, we will take this coefficient vector, time reverse it and complex conjugate it, and therefore, if you form the numerator as a n star plus a n minus 1 star z inverse, a 1 star z to the minus n minus 1 plus z to the minus n. This is an nth order all pass filter, and it is an important exercise for you to show, starting from this, that this indeed gives you unit magnitude response. This is a simple exercise you can do based on what I have learned so far. And any nth order all pass filter can be written as product of n first order all pass sections. Therefore, this can be written as k going from 1 to cap n 1 minus pk z inverse, and the numerator is minus pk star plus z inverse. So, each section is all pass, but it is first order, and if you cascade n such first order all pass systems, you will get this nth order all pass system as given here. Notice that the inverse of an all pass system is also all pass, because the magnitude response is unity. The inverse system also will have unit magnitude. Let us go and revisit this first order section to get a feel for what is going on. So, it has a pole at z equal to a, the 0 is at 1 over a star. Therefore, if the pole is at a here, then the 0 must be exactly at its reflected position. Therefore, if you have r e to the j theta being the location of the pole, then 1 over r e to the j theta must be the location of the 0. Therefore, if you had an all pass system, for every pole there must be a 0 at the reflected position. Yes. So, reflection around the unit circle. Yeah, the distances won't be. So, this is different from the reflection that you are used to saying reflecting something about the y axis. There the distances will be maintained, right. Whereas here what we mean by reflection is, if you had r e to the j theta, the reflected root about the unit circle is 1 over r e to the j theta. So, here we are not meaning the distances have to be maintained. So, this is the simple first order all pass section, the pole 0 configuration. And note that if this were all pass, its inverse system also will be all pass. And in that particular case, you will have a pole here and a 0 here, because if you take the earlier system and then if this were h of z, if you considered 1 over h of z, poles will become zeros, zeros will become poles. Therefore, this is how the pole 0 plot will look for a first order all pass, which is the inverse of the earlier system. The point to note is, if you want all pass systems to be both causal and stable, your only choice is this, because it is only this choice that gives you poles that are strictly inside. If you want this also to be stable, the system has to be anti-causal, and in practice you want causal and stable filters, and hence the all pass filter will have poles strictly inside the unit circle, and for every pole inside the unit circle you will have a reflected 0. These are very important building blocks in practice. These are used for phase compensation. And the term itself kind of gives you a hint as to what this is going to do. If you cascade an all pass system with another system, the overall magnitude response is not going to change, because the magnitude response of the all pass is unity. All it can do is change the overall phase response. The original phase response will get added to the all pass system's phase response, and later when we talk about group delay, you will learn that certain phase responses are desirable, and if your original system has a phase response that is not what you want, you can alter the overall system's phase response by cascading that system with this all pass, and you have to design the all pass such that the overall phase response is desirable, and that is what phase compensation is. So, it is one of the uses for all pass is that. The other important use for all pass is it is used as a building block for building more complicated filters. For certain filter types. And to give you a feel for what this means, if you had an all pole filter that can always be expressed as a sum of two all pass sections. An all pole filter can always be represented as a parallel combination of all pass sections. And why is it that you want to do that? Again, to get a feel for why that might be desirable is that, remember, in practice, whenever you have coefficients, when you are implementing it, you are going to quantize them. So, when you quantize, you no longer have the original system, but only an approximation. And if you look at this, typically we will be interested in real valued impulse responses, which means all the coefficients will be real valued, and you can always build a real valued system as cascade of first and second order building blocks, because if we had two complex conjugate poles, you can combine them and form a single second order system with real valued coefficients. Therefore, in practice, if you now consider all these coefficients to be real valued, so Pk star will really be Pk for a first order section, and for a second order system you will have a second order denominator and a second order numerator, but the coefficients will be time reversed. Therefore, the numerator coefficients and the denominator coefficients are not independent. You can realize them using just one set of coefficients, because the same set of coefficients will be used in the numerator as well. Therefore, when you quantize, you are not quantizing independently the numerator coefficients and the denominator coefficients. Therefore, this is where the quantization advantage comes about, when you realize these all pole filters as made up of all pass building blocks. So, these are just a couple of examples of uses of all pass, and there is a full paper by P.P. Vaidyanathan and couple of other authors. The title of the paper is All Pass Sections, a Versatile Building Block. Google Bhagavan, if you just type Vaidyanathan, All Pass and Versatile, lo and behold you will get that paper as the first hit, and you can look that up. So, this is just to give you a feel for what all pass sections can do for you.